Hello guys, welcome to this lecture. This is 5-5A. Note that this is not a live lecture, as you can tell by the time on my screen. So we're just going to be covering the first half of 5-5, and then the next half we'll cover, I think, when we get back from break. Okay, so in this lecture we're going to go over two groups of formulas that we do need to memorize. The first of which are the double angle formulas, and the second of which are the power reduction formulas. So let's start with double angle formulas. The good news is that these formulas are very easy to memorize because they are very straightforwardly derived from our addition formulas. Okay, and I'll explain how. So double angle formulas have to do with how we express, for example, sine of 2x in terms of sine x and cosine x, or cosine 2x, or tangent 2x. Okay, and as you can see, these are very easy to derive because 2x is simply equal to x plus x, right? Sine of 2x is equal to sine of x plus x, and so that means we can very easily apply the sine addition formula. So sine of x plus x is going to be sine of x times cosine of, not y, but in this case x, plus sine of x times cosine of x, which is really just equal to 2 sine x times cosine x. The same is true for cosine of 2x. That's just going to be cosine of x plus x, which is cosine of x times cosine of not y, but x here, minus sine x sine x. And so we would express this as cosine squared x minus sine squared x. Okay, and so these final forms, those are the double angle formulas. You can see how straightforward they are. And then tangent x is just tangent of 2x. Tangent of 2x is tangent of x plus x, which is equal to, right, tangent x plus tangent x in the numerator, all over 1 minus tangent x times tangent x, right? In all of these cases, we've simply replaced the y in our addition formulas instead with the x. And so that means tangent x plus x is 2 tangent x over 1 minus tangent squared x. Okay, and so those are going to be our double angle formulas. I'll write this a little more concisely on the bottom. Okay, double angle formulas, they do have to be memorized. Sine of 2x is 2 sine x cosine x. Cosine 2x is equal to cosine squared of x minus sine squared of x. And then tangent of 2x is equal to 2 tangent x over 1 minus tangent squared x. Okay, so make sure you have those memorized. Now, there are also two different ways of actually writing the cosine 2x. So the cosine double angle formula has two different ways of expressing it. And sometimes they are slightly more useful for our purposes, although you don't have to memorize them because they're easy to derive. Okay? And let me explain what they are. So cosine 2x, typically we express this in the way we've just done, which is cosine squared of x minus sine squared of x. Okay, but let's say we wanted to express this only in terms of cosines and not sines, right? Because in some cases, right, suppose we're solving an equation that has a lot of cosine x's, we don't want any sine x's, And so we only want to express it in terms of cosine sometimes. Well, what we could do is simply replace that sine squared here with a 1 minus cosine squared, right? Because sine squared plus cosine squared equals 1, right? Remember that. And so that means sine squared equals 1 minus cosine squared, right? We should have that down pretty well now. And so that means we can replace that sine squared like this. So we would have cosine squared minus, in parentheses, 1 minus cosine squared x. And then if we rewrote this, that minus sign would distribute. This becomes cosine squared x minus 1 plus cosine squared x, which is equal to 2 cosine squared x minus 1. Okay, so that's sometimes a different way that people use to write the cosine double angle formula. And it's also valid, and we want to use that one when it's more helpful. Similarly, we can actually also write the cosine double angle formula in terms of sines only. Right? Why is that? That is because cosine squared, just like sine squared, cosine squared can also be written only in terms of sine squared. Right? Cosine squared is 1 minus sine squared, analogously to the previous case. And so if we replaced that cosine squared with a 1 minus sine squared, we would get this, 1 minus sine squared in parentheses, minus sine squared. And this would come out to 1 minus 2 sine squared x. Okay? And so these three ways of writing the cosine double angle formula, right? The first one being here, that's probably the most common way of seeing it. And then this one's the second way, and this one's the third way. Okay, so those are three equivalent ways of writing cosine 2x. And that only applies for cosine. So sine and tangent, those are typically only represented in this way, right? For sine 2x and tangent 2x. But cosine 2x is a little special in that we can write it in three different ways depending on what kind of purposes we want to use it for. My personal recommendation is to maybe avoid memorizing the second and third ones, just because you probably have limited bandwidth right now. And I would focus on having this memorized and then just knowing how to derive the second and third ways based on this method, which is not very hard, right? Okay, let's do some example questions that utilize what we've learned here. In general, they're pretty straightforward applications that simply make use of what we've already learned in the previous lectures. So the first example that the textbook has for us is having us solve this equation. So we have 2 cosine x plus sine 2x equals 0. Okay? And so we see we have a sine 2x here, and so that probably means we should use the sine double angle formula that we just learned. And so we're going to replace that sine 2x with a 2 times sine x cosine x. So that becomes 2 cosine x plus 2 sine x cosine x. And now we've successfully written everything in terms of only sine x and cosine x, right? No more double angles. And so that's something that's much easier for us to work with when we want to solve for x. Okay, now the next step is we can factor this actually. And that's always something we want to do when we have an equation that equals 0. We want to factor because after factoring, we'll know that in order for that entire equation to equal 0, that means at least one of those factors has to equal 0. And so that'll give us x. So in this case, we can factor out a factor of 2 cosine x from both terms. And so if we divide both terms by cosine x and take that to the front of the equation, we're going to be left with 1 plus 2 sine x in that factorization. All right, I just divided both terms here by 2 cosine x, which left me with a 1 in the first term, which I've left here, and the second term leaves a 2 sine x. Okay, now because I have two different factors that are being multiplied together to equal 0, that tells me that at least one of them has to be 0. All right, and so I can split it into two cases. My first case is that 2 cosine x equals 0. In my second case here is that 1 plus 2 sine x equals 0. All right, and so case 1, that tells me that cosine x equals 0. And in case 2, if you just do the algebra, that tells you that sine x equals negative half. Okay, and so now these are questions that are not hard for us to solve. We've done them a lot. In order for cosine x equals 0, all right, we're going to go to our unit circle. That means that we're looking for points on the unit circle with x coordinate 0, right? Because cosine is the x coordinate. And so that's going to be this point and also that point. So that corresponds to x equals pi over 2 and x equals 3 pi over 2. All right, and we're going to remember, because the period of cosine is 2 pi, we're going to add those 2 pi n's, where n is some integer. And that'll give us the set of infinite solutions. Okay, so those are our two solutions for case 1. And then for case 2, we're looking for points on the unit circle with y coordinate negative half. Okay, so y coordinate because sine corresponds to y. And so we're looking for this point and that point, right? Points that have a y coordinate of negative half. Okay, well, if it's going to be half, that means we know it has to be a multiple of 30 degrees. And we also know that half is kind of like the shorter one compared to the longer side, which is root 3 over 2. And so that tells us that this angle here is going to be 30 degrees, and this angle here is also going to be 30 degrees. Okay, so we know that this point here is actually going to be 180 degrees plus another 30 degrees. And so that's pi plus pi over 6, or 7 pi over 6. And then by similar logic here, this one is 2 pi minus pi over 6, which is 11 pi over 6. Or you could also have said negative pi over 6. So that tells us that x equals 7 pi over 6 plus 2 pi n, or x equals 11 pi over 6 plus 2 pi n. And those would be our two answers. Okay, so in total we have 4 answers, and we didn't do anything bad or illegal. We didn't square both sides, we didn't multiply by cosine or sine, and so we know that we're not going to have any extraneous solutions, and so we would be done. We could be extra safe and go back and plug in all 4 of these solutions, but we don't have to. Okay, so that's the first example, and you can see the only new step was really just converting that sine 2x into a 2 sine x cosine x, and the rest is stuff we've learned from 5-3. I'm going to go through another example that's very similar, but if you feel confident with this, you can also just skip it and move on in the recording. The other example I'm going to do is cosine 2x plus cosine x equals 0. Okay, this is not the same as the classwork, okay, so this is not going to give you the answer to that, but hopefully it will be helpful. So, we see a cosine 2x, and so that indicates that we should probably use the cosine double angle formula, and so we're going to do that. We're going to replace cosine 2x with cosine squared x minus sine squared x, right? Because this is the double angle formula for cosine, and then plus cosine x equals 0. Okay, so now we've successfully written it in terms of cosines and sines of single angles, so just x, but the problem is there's no straightforward factorization here because we have a mix of different trig functions, right? And so that tells us that we're probably going to have to convert that sine squared into a cosine squared, right? And so we're going to use the fact that sine squared equals 1 minus cosine squared. Right? I'm choosing to convert the sine squared because I know I have a cosine here. And, you know, I could have tried to convert this cosine squared into sines, but the problem is I would still be left with a cosine here, which I can't easily convert into a sine because it's only a single power of cosine, which I have no good formula for. And so that's why I chose the sine squared to convert to a cosine squared. Okay, just kind of the reasoning behind that. So because sine squared equals 1 minus cosine squared, I can make that substitution. And I'll have cosine squared x minus, parentheses, 1 minus cosine squared, which is just sine x, plus cosine x equals 0. All right, and then if I distribute this minus sign, I get a plus cosine squared. And so combined with this cosine squared here, I'm going to have 2 cosine squared x minus 1 plus cosine x equals 0. Okay? And actually, you know, interestingly, at this point, you may have realized that this was one of the double angle formulas that we had above, right? Cosine 2x equals 2 cosine squared minus 1. And I kind of simply took the circuitous way in getting that formula, when in reality, I could have just looked at my notes and realized that cosine 2x equals 2 cosine squared x minus 1. So that's why sometimes it is helpful for us to have these memorized if we want to be able to just quickly convert it into that form. All right, because in this case, because we had a cosine x in our equation, right, it would have been helpful for us to have a double angle formula that only contains cosines. And that's exactly what we have in reality, right? And so that's why sometimes it is helpful to have this formula in the back of your head. But if not, you know, as you can see, we didn't really have much trouble just deriving it on the spot. So it's up to you whether you want to memorize it or not. All right, now we have an equation with only cosines, and you'll notice that it's not hard to factor because it's a quadratic in terms of cosine. I'll write it more clearly with the cosine on the left side of the minus 1. So this is also 2 cosine squared x plus cosine x minus 1 equals 0. Okay, and so this is something that we can simply factor as a quadratic. If it's more clear to you, I can write it in terms of, you know, making the substitution, y equals cosine x. And so this would just turn into 2y squared plus y minus 1 equals 0. Right? And that's something we know how to factor. We're looking for two numbers that multiply to negative 2, right? A times c. Multiply to negative 2 and add to 1. So that's going to be 2 and minus 1. That means we can factor by grouping, split this into a 2 and a minus 1. So that becomes 2y squared plus 2y minus y minus 1 equals 0. And then we can factor by grouping, right? Factor out a 2y here, factor out a minus sign. And I'm going to be left with 2y minus 1 times y plus 1. All right, and then I can plug those cosines back in. That gives me 2 cosine x. Let's write that neatly. Two cosine x minus 1 times cosine x plus 1 equals 0. All right. So once again, we have two factors that are being multiplied to equal 0. So that tells us that we really have only two cases. The first case is that 2 cosine x minus 1 equals 0. And the second case is that cosine x plus 1 equals 0. All right, so the first case tells us that cosine x equals 1/2. And then if we solve this using the same process as before, right, 1/2, that's here and here for the x coordinate. That tells us that x is going to equal pi over 3 plus 2 pi n and minus pi over 3. Or you could also say 5 pi over 3 plus 2 pi n. So those are two solutions for case 1. And then for case 2, we have cosine x equals minus 1. And so that means that on the unit circle, we're looking at this point, right? X equals minus 1. Sorry, x coordinate minus 1. So that tells us that x is going to equal pi plus 2 pi n. And that's going to be our only solution for case 1, case 2. And so in total, we have 3 solutions, 3 groups of solutions, and we would be done. All right, let's go on to the next topic, which is power reduction formulas, or power reducing formulas. Power reducing formulas. Okay. And let me kind of explain the motivation behind these formulas. So these formulas help us to write sine squared of x in terms of only cosine 2x. Okay, I'm not saying these are equal, but I'm saying that it helps us to write sine squared in terms of what we call a single power of cosine. So no more squares. These formulas would also help us to write cosine squared in terms of cosine 2x, or tangent squared in terms of cosine 2x. Okay, so the idea is that we're reducing the power. We're getting rid of the squared. And this is something that's very useful in calculus when you do integrals. And so that's something you'll encounter later, which is why we're doing it now. Okay, let me explain how we can get these formulas. Okay, so I'm going to erase this because it's not important. How do we get these formulas? Well, the idea is we're kind of inspired by our different formulas for cosine 2x, okay? So if you remember from our notes, we had those second and third formulas for cosine 2x, right? This one and this one. Let me write those again down here. Cosine 2x is equal to 2 cosine squared x minus 1, and it's also equal to 2 sine squared x. Sorry, that's not right. It's also equal to 1 minus 2 sine squared x. Okay. And so kind of the motivation is that if we did some algebraic manipulation, right, we can isolate that cosine squared, or we can isolate that sine squared. And that would allow us to write cosine squared and sine squared only in terms of cosine 2x. Okay, so if we did that for the first equation, we could move the, maybe I'll just start with the first equation, go top down. We could move the 1 to the right side, and we would have cosine 2x plus 1 equals 2 cosine squared x, right? And then if we just divide both sides by 2 and move it and kind of switch the sides, if we divide both sides by 2, we're left with our power reduction formula. Okay, so this is our first power reduction formula for cosine. Cosine squared equals cosine 2x plus 1 over 2. And the idea is that it helps us to write cosine squared in terms of only single powers of cosine. The same can be done for sine squared. So for sine squared, we would start first from our cosine double angle formula. This time we're going to use the third one, 1 minus sine squared. Sorry, that's 1 minus 2 sine squared. 1 minus 2 sine squared. And then if we rearrange terms, so perhaps we can move the 2 sine squared to the left side, and then the cosine to the right side, that would give us 2 sine squared equals 1 minus cosine 2x. Right, I just switched slides for those. And then if I divide both sides by 2, I'm left with my power reduction formula for sine squared, which is 1 minus cosine 2x over 2. Okay, so these can actually be written, maybe a little more symmetrically if I replace the order here with 1 plus cosine 2x. Okay, same thing, just change the order. So as you can see, for both of them, you're going to have a fraction, right? There's everything's over 2 for both of them. You're also going to have a 1 that's being added. The only difference is that for cosine squared, you have a plus cosine 2x. Whereas for sine squared, you have a minus cosine 2x. So that's really the only difference. Personally, I would recommend memorizing this because it's a little harder to derive than some of those other ones, right? It takes a few more steps. So I would recommend having these memorized, and that will be very helpful for you in calculus. And also on the test, of course. Okay, so that's cosine squared, and that's also sine squared. Now you might be wondering, is there a tangent squared? And the answer is yes. But we simply derive it differently. Okay, tangent squared x also has a power reduction formula. But we simply do this by rewriting tangent squared as sine squared over cosine squared, right? And then we would just plug in these formulas that we just derived. Right, so sine squared is 1 plus cosine 2x over 2. And then cosine squared is 1 minus cosine 2x over 2. And so that those over 2's, they both cancel out. And so we're left with tangent squared equals 1 plus cosine 2x over 1 minus cosine 2x. Right? And, if you have sine squared and cosine squared memorized, then this is pretty easy to memorize as well, right? Oh dear, I've mixed up the pluses and minuses. Very sorry. It's not good. Hopefully nobody stopped watching before that. But yeah, right, sine squared is 1 minus cosine 2x. Cosine squared is 1 plus cosine 2x. So the minus is on top and the plus is on the bottom. Okay, sorry for that mistake. And yeah, if you have sine squared and cosine squared memorized, tangent squared is not something you would need to memorize because it's easy to derive. All right, let me do an example. This is quite similar to the classwork. And the homework question is actually simply just a harder version of this, but you'll get there. So the question on the classwork is to write sine to the fourth of x in terms of first powers of cosines. Okay? And so, this is where power reduction really comes in, right? Because here we not only have a sine squared, we actually have a sine to the fourth power. And so this kind of demonstrates really the power of power reduction, no pun intended. So the way we're going to approach this, and this will apply on the classwork as well. Classwork has cosine to the fourth x, not sine to the fourth. The way we're going to approach this is by writing sine to the fourth x as sine squared squared, right? If we square square, we get a fourth power. So that's very easy to see that this is true. And then now we can apply that power reduction formula, right? Because sine squared x equals 1 minus cosine 2x. As you can see, they're not very fresh in my memory either. All right, so sine squared x is equal to 1 minus cosine 2x over 2. And that's all squared. All right. And so now the idea is that we're going to keep expanding this. And then if we encounter any more squares of trig functions, we can just do another power reduction, right? And so we're going to expand this. And the way to expand this is by squaring the numerator and then squaring the denominator. So when we square the numerator, we're going to get 1 minus 2 cosine 2x plus cosine squared of 2x. Right, here I simply use the formula a minus b squared equals a squared minus 2ab plus b squared. Okay. And then the denominator is going to be 4. That's 2 squared, right? Okay, so I'm not done yet because the question asked me to write it in terms of first powers of cosines. Okay, but here I still have a cosine squared. And so that means I'm going to have to use another power reduction. All right, the only difference here is that I have a 2x in the argument and not a single x. And so that means I'm going to have to plug in, right, if I recall my power reduction formula for cosine squared of x, that's 1 plus cosine x, 1 plus cosine 2x over 2. All right, and so if I wanted to find cosine squared of 2x, you can see just by analogy that this is going to be equal to 1 plus cosine of 4x over 2, right? It's like I'm simply replacing this x here with that 2x, right? It's like this 2x is going into the x, and so that means this 2x would become a 4x. That's how we get that. Okay, and then I'm simply going to plug this in back into here, and that is going to give me this new thing. Okay, I'm going to have, and here it's best to divide the 4. So divide everything on the numerator by 4. And so split it up into multiple fractions. You're going to get 1/4 minus 1/2 cosine 2x. All right, divided that -2 by 4. Gives me -1/2 plus 1/4 of cosine squared. All right, 1/4 of cosine squared. But what is cosine squared of 2x? That's right here, right? 1/4 of cosine squared 2x is going to be 1/4 times 1 plus cosine 4x over 2. Okay? And so now I can keep expanding this. I can expand that 1/4, distribute it over that fraction. That's going to give me 1/4 minus 1/2 cosine 2x. All right, and here I have a 1/2. So when I multiply by 1/4, I get 1/8. And then the other term here is a 1/8 cosine 4x. And then I can combine the 1/4 with the 1/8 here, and I'm left with 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x. And so that's successfully in first powers of cosines. Okay, and so this tool is very powerful for calculus whenever you want to do an integral. But, that'll come later for you guys. I'll stop there, and hopefully this is helpful. Have a nice homework time.